Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 26 of the Statistical Thermodynamics course. So this time our main focus will be on spectroscopic term symbols for multi-electron atoms. Okay. So that would be the first thing that we will do here. Okay. So the electronic configuration now, okay, let's look at it now in a little bit more details. Okay, so we can do this lecture. So basically four quantum numbers are used to determine okay, the electron configuration okay, but that is what we saw in the last lecture. But however, this configuration okay, does not account for, these configurations do not account for significant interactions among the various orbital and spin angular momentum vectors of a multi-electron atom. Okay, so though the four quantum numbers are essential and they are used to determine the electronic configuration, but they are not enough because there are significant interactions around the various orbital and the spin angular momentum vectors. Okay, so these interactions can be therefore modeled. These additional interactions can be modeled by introducing the resultant. Mark the word resultant, okay, orbital and spin angular momentum vectors. Right, the resultant orbital and spin angular momentum vectors. Okay, so this means L is summation of Li over I. S is summation of Si. Okay, where Li and Si, what do they indicate? They indicate the corresponding individual vectors for each electron, which we already know. Okay, so now, this is the first step that we did. Now we can draw an analogy from, if you look at equation, let's give you the rewrite the equation once again. So if you recall that L square was L into L plus 1 into h bar square and s square equal to s into s plus 1 h bar square. If you recall these two, okay, so therefore now using these two or invoking them, okay, we can say and write it, the magnitudes, okay, for the orbital spin angular momentum vectors as HR and S equal to S plus 1 H bar. Okay, so here where L and S are the resultant orbital and spin angular momentum quantum numbers. Respectively. Okay. Now, if we introduce the spin orbit coupling, which is also called Russell-Saunders coupling. Okay, which dominates for multi-electron atoms with Z less than 40. Okay, so we can write the total angular momentum vector as J equal to L plus S. Okay, so because of this coupling, because of the spin orbit coupling, okay, because of the spin orbit coupling, the orbital spin and total angular momentum exercise a pronounced effect on the allowed energy levels and thus the spectrum. So because of this and the orbital, because of the spin orbital coupling, the orbital, then spin and total angular momentum vectors, okay, exercise pronounced effect allowed energy levels, and consequently the spectrum of multi-electron. Okay, multi-electron atom. Okay, so the spectroscopic classification is a nomenclature basically, and it provides a scheme for labeling these energy levels. So if you just look at the Russell-Saunders, what we mean, so this is like draw it like this. So this is like the J. Okay, so this L. So this is like the vector model for this Russell-Sanders coupling. Okay, so the coupling. So that coupling can be also understood, that a coupling between such vectors. So it's basically between such vectors introduces what we call a natural torque. So N, L, and S will precess about J. So L and S, as you can see, this is S. So S and L, they precess about J. Okay, this induced precession, this, because of this precession is like this, so it produces this precession, right, because of this coupling and because of this precession. Okay, this precession okay, affects, this precession affects the electronic energy, okay, of multi-electron system, electron atom. Got it? So so because of this because of this coupling, the total angular momentum vector becomes quantized. Because of this coupling, okay, the total angular momentum vector becomes quantized. So okay, so J is equal to L minus S plus 1, L plus S minus 1, all the way up to L plus S. JZ, which is basically, we'll see what that is, Mj H bar. Mj is minus J plus 1, J minus 1, J. So J is the total angular momentum. Mj is obviously the quantized Z component. J. Okay. So various permitted values of J, okay, reflect the process of vector quantization. Reflects process of vector quantization. And we can give a picture to demonstrate that. Okay, so let's look at this picture. Say J is equal to 2, L, this is S. Okay, so this is for L equal to 1, S equal to 1. Okay, then J equal to 1. Okay, so L is like this. Okay, S will be like that. This is J. Then J equal to 0. It's like this. Okay. So this is like additive because these two are unity. So this is 2, same direction. These are all unity. So therefore this is j equal to 1 and this is j equal to 0. So this is how the L and S, if they are all unity, so this is the way the vector quantization actually happens. So the electronic energy of a multi-electron system is primarily determined. So we can say that the electronic energy of a multi-electron system, multi-electron atom, is determined mainly by N and L values, okay, for each electron, which was the shell and subshell concept that we had, that SPDF. But overall, okay, electron cloud, if we consider the electron cloud as described by L, S, and J, this is important secondary effect, right? So this is an important secondary effect when the electron cloud, okay. Therefore both, so what we require the electron configuration, okay, and also the associated and the associated angular momentum quantum numbers, okay. These two are required to basically properly specify okay, an electronic okay, energy level. These two are required for specifying the electronic energy level. Moreover, it should be noted now that okay, that the total angular momentum quantum number J influences electronic energy, while its Z component MJ does not, right? While its other component that does not. Okay, the electronic degeneracy GEL equal to GJ is equal to 2J plus 1. Okay. The term classification for the electronic state of a multi-electron atom is predicted by the need to specify L, S, and J. Okay, so in general, atomic term symbol is given in this form: 2s plus 1 Lj. So L equal to 0, 1, 2, is equivalent to saying S, P, D, F. Okay. So if L equal to say 1 and S is equal to plus half, okay, then what will be J? J will be half and 3/2. J, we already have designated what is J going to be here. Okay, that is your J. All right, so that is the J. Okay. And therefore the total degeneracy is also 2J plus 1. So J is this. Hence the relevant term symbols will be okay, for this particular case is 2P half and then 2P 3/2. Okay, so in other words, this is also has got a fancy name. This is called the doublet P states. Okay, so this is the characteristic of all alkali metals like sodium and potassium. Okay, so the electronic level of an atom requires a specific term symbol. Okay, so for completeness, now if we take if you write the ground electronic state for all the 18 elements that is there in the book, table 6.6, can be consulted. We know that for any completed subshell, the Z components of L and S, this is the sum total. By definition, ML is equal to summation M Li equal to 0, and MS summation over I MSI is also equal to 0. Okay. As a result of this, L is equal to S is equal to 0. So the associated term symbol for any, so associated term symbol for any completed subshell any completed subshell is 1S0. Got it? Because that is 0, L equal to 0. Okay, and if you look at the nomenclature, S equal to 0. Okay, so that is 1, and then J obviously is equal to 0 as well. Okay, so therefore we may safely ignore all quantum numbers affiliated with completely filled inner subshells when determining the relevant term symbols. So for the relevant term symbols, we just need the unfilled subshells, so to say. Okay, so this is also given. For example, let's take an example. Okay, say for Z equal to 11. Okay, so that was sodium, right? So the term symbol in this case will be 2S half. Okay. Similarly, if Z is equal to say 18, the term symbol will be 2A. Sorry. Term symbol will be 1S0. Okay. Similarly, if it is Z equal to say 16, okay, the term symbol will be 3E2. these are the different term symbols that we can write, okay, because of this. The empirical rules for all these things. So you can, so as I said earlier, that if we take safely ignore, okay, let me write it here, that we can safely ignore all quantum numbers, okay, affiliated with completely filled inner subshells when determining the relevant term symbols. So you can, I have shown a few examples of it here, that this is what it is, okay, and therefore the term symbols can be associated in the way that we talked about. So in the next one, we will do the electronic energy levels and the degeneracy for atoms. But before that, just take a look that, you know, for any completed subshell, okay, this particular relationship is valid, okay, which leads to L equal to S equal to 0. So that means you don't need to consider those filled inner shells when you determine the relevant term symbols, okay? So in the next class, we will take a look about that what are the other, what is the electronic energy levels and the degeneracy for atoms, and we will take it forward from there. Thank you.